Before the 1st of July, 2025, interstellar visitors seemed like a solved problem. We had seen two before, built models to explain them, and trusted that our telescopes could capture whatever details the cosmos chose to send our way. But then came 3I, and certainty melted away like frost under a rising sun. What we found defied expectation. A nucleus too small to sustain such fury, yet it vented carbon dioxide at levels that border on the impossible. Its coma ballooned outward until calculations showed it spanning distances larger than Earth's own orbit. The spectra it returned spoke in dialects no planetary nursery should produce, chemical fingerprints that match no formation environment we know. Each dataset raised more questions than it answered, pulling apart assumptions we thought were bedrock science. The paradox is humbling. The most powerful instruments ever built, Hubble's sharp eyes, Webb's infrared vision, radio arrays tuned to cosmic whispers, have been brought to bear on an object barely larger than a city, and still the mystery deepens. What does it mean when our finest science falters before something as unassuming as a comet? This is where our journey begins, with the possibility that 3I is either the most consequential discovery of our generation, or a reminder that the universe still guards secrets we are not yet prepared to unravel. Part 1. Why 3I just doesn't make sense. On the 1st of July, 2025, at precisely 14:37 Universal Time, something shifted in humanity's understanding of the universe. Not through a distant quasar or a buried data table in a graduate thesis, but in our own solar system. The Atlas Survey Station in Chile, an automated telescope built for the routine, almost mundane task of spotting hazardous near-Earth asteroids, picked up a faint, unremarkable smudge. A moving dot 4.5 astronomical units from the Sunday. At first, it seemed no different from the thousands of rocks catalogued each year, but within hours, the orbital solutions told a very different story. The object was not bound to the Sunday. Its eccentricity was far greater than one, the unmistakable fingerprint of a hyperbolic orbit. In the language of celestial mechanics, this meant one thing. It had come from interstellar space, and once it passed perihelion, it would leave us behind forever. The formal designation, C divided by 20, 25, N1, Atlas, quickly gave way to a simpler, more evocative name among astronomers. 3. The third confirmed interstellar visitor after Oumuamua in 2017 and Borisov in 2019. The first clue to its strangeness was its speed. 130,000 miles per hour, over 209,000 kilometers per hour, a velocity unmatched by any solar system object we have recorded. For comparison, take the speed of a high-powered rifle bullet and multiply it by more than 170. That was Atlas, shrieking into our neighborhood with the momentum of another star system. But velocity was only the beginning of its puzzles. Within days, the Gemini North Telescope in Hawaii captured its first detailed look. Expectations were modest, perhaps a cold, inert shard of rock, battered by radiation, a survivor from interstellar exile. Instead, the images revealed a halo of activity, a compact coma of gas and dust wrapped around an invisible nucleus. Atlas was not dead, it was alive with energy, sublimating volatile ices into space as soon as the sun's warmth touched it. In one instant, our mental image of the object shifted from frozen relic to breathing wanderer. That realization carried weight. Here was a body that had spent untold millions of years drifting between the stars, enduring temperatures a fraction above absolute zero, bombarded by cosmic rays powerful enough to sterilize anything we know. And yet, when it reached the outskirts of our system, it responded instantly, releasing vapor as though it had been waiting for this moment. Atlas was carrying chemistry across light years, sealed in its core until our star awakened it. But the strangeness did not stop there. Its trajectory cut through our solar system with uncanny precision. The closest approach would be about 1.8 astronomical units, nearly 270 million kilometers, well clear of danger, but close enough for sustained observation. Safe for Earth, yet almost too perfect for science. To many, it felt like the cosmos itself had threaded a needle, placing an interstellar object in just the right corridor where every major observatory could track it. NASA and ESA moved quickly. Hubble was reassigned. Webb received priority slots. The Swift Observatory, TESS, and arrays of ground-based telescopes turned their gaze toward Atlas. This was no longer a curiosity to file away in the Minor Planet Center's archive. It was a messenger from another stellar nursery, carrying chemical records of conditions alien to anything in our local environment. And yet, the more we looked, the less sense it made. Hubble tracked its coma, expanding far larger than expected for a body of its estimated size. Webb's infrared spectra revealed ratios of carbon dioxide to water that defied cometry models. Ground-based telescopes struggled to reconcile the observed brightness with plausible nucleus dimensions. Every observation opened new gaps between theory and data. The irony was impossible to miss. A wanderer from light years away, drifting into our skies, offering itself to our scrutiny for a fleeting season. We had months to study what had traveled for billions of years, and with each new dataset, the mystery only deepened. Was Atlas typical of interstellar comets, or an outlier? Did its chemistry point to exotic formation zones, or had radiation sculpted it into something unrecognizable? The object refused to fit into neat categories. By August, detailed images and spectra poured in. Teams compared notes across continents. The conclusions converged on one simple truth. I wasn't going to surrender its secrets easily. It was a paradox in motion, a comet that shouldn't exist, active when it should be dormant, carrying chemical fingerprints that didn't match any environment astronomers could model. And so began the race. A race not against Atlas itself, it was indifferent to our attention, but against time. In months it would fade, shrinking into the black as it receded toward the outer planets and beyond. For now, it lingered just long enough to confront us with questions sharper than answers. What is it? How did it form? And why does it look nothing like what our best theories predict? The stage was set. Atlas was here. Our instruments were ready, but the mystery had only begun. Part 2. The path through our neighborhood. Imagine the solar system as a giant clockwork, every planet a gear tracing its orbit with flawless precision. Into this intricate mechanism enters a foreign bullet, not from a nearby star, but from the deep galactic wilderness. That bullet is 3I, and its passage through our neighborhood reads like choreography, too precise to be accidental, though written by physics long before Earth itself was born. The script is striking. Perihelion, the closest approach to the Sun, falls on the 29th of October 2025. Atlas will swing between the orbits of Earth and Mars, just 130 million miles from our star. At that distance, the Sun's radiation is fierce enough to boil away ancient ices, yet not close enough to annihilate the nucleus outright. It is a razor-thin balance, destruction on one side, revelation on the other. And yet, at the very moment of maximum activity, Earth will be on the opposite side of the Sunday. For nearly 2 months, from late September through early November, the object will be lost in glare, invisible to every telescope on or around our planet. Cosmic irony at its most merciless. That geometry imposes a cruel deadline. Astronomers will have roughly 3 months of clear viewing before Atlas disappears into solar brilliance, followed by perhaps 6 weeks after it re-emerges in December, before distance dims it beyond serious study. This is not a long campaign. This is a sprint against time, a race to extract as much knowledge as possible from a visitor that will never return. Yet the trajectory offers gifts alongside frustrations. On the 3rd of October, Atlas will brush past Mars at just 29 million kilometers closer than Phobos, the inner Martian moon, ever comes to the red planet. For the robotic fleet stationed there, from the veteran Mars Reconnaissance Orbiter with its high-rise camera to the younger orbiters and surface rovers. This represents a once-in-a-lifetime chance to view an interstellar visitor from alien ground. Images captured from Martian skies could become iconic. The first photographs of a star-born wanderer taken by machines on another world. Geometry defines astronomy, and here, geometry is both curse and blessing. When Atlas finally reappears to Earth's telescopes in early December, it will rise in the pre-dawn sky among the stars of Virgo, sliding upward toward Leo. But the reprieve is fleeting. By then, it will be fleeing the sun at more than 150,000 miles per hour, fading night by night as it slips back into the cosmic sea. Amateur astronomers may strain to glimpse it, but expectations must remain modest. Even at peak brightness, Atlas is unlikely to exceed magnitude 11 or 12, a faint smear requiring serious equipment. There will be no brilliant spectacle across the heavens, no cometary tail bright enough to dazzle the naked eye. This messenger prefers subtlety. The orbital mechanics themselves add another layer of intrigue. Atlas is not just moving quickly, it is moving strangely. Its hyperbolic excess velocity is about 25 kilometers per second, relative to the local standard of rest, fast enough to escape not just our solar system, but the gravitational influence of nearby stellar groups. This is not a recent exile from a neighboring nursery. This is a body that has been wandering for unthinkable epochs, its path sculpted by countless stellar flybys, its chemistry frozen testimony from an era billions of years before humanity existed. As its outbound leg unfolds, further opportunities tempt engineers. In March 2026, Atlas will make a distant pass near Jupiter. Already, proposals circulate within NASA. Could Juno, the spacecraft orbiting the gas giant since 2016, be redirected for a long-shot intercept? It is audacious, repurposing a probe designed to study Jupiter's interior and magnetic field into humanity's first close encounter with an interstellar visitor. The challenges are formidable. Fuel reserves, orbital mechanics, and timing must align perfectly. Success would mark an extraordinary pivot in space exploration, turning contingency into history. And yet, beyond the technical calculations, Atlas forces a humbling reflection. Here we are, a species wielding billion-dollar instruments, coordinating across continents, marshalling the finest minds in planetary science, all to observe a wanderer that will grace our skies for less than 2 years before vanishing into darkness. The object itself is indifferent. It will continue its journey, whether we watch or not. The urgency belongs entirely to us. The path of 3I is not merely a line plotted on charts. It is a schedule of opportunities and losses, of windows opening and slamming shut according to immutable celestial mechanics. Every night that passes brings us closer to the last chance, the final observation before the wanderer slips forever into the galactic night. Our challenge is to read as much as possible from this brief visitation, to let the data speak before silence returns. In that sense, Atlas is more than a comet. It is a test of our technology, our coordination, and our imagination. The question is not only what we will learn from this messenger, but whether we will learn enough before the window closes. Part 3. First Looks, What Hubble Sees. On the 21st of July, 2025, the Hubble Space Telescope turned its patient gaze toward 3I. What returned was a paradox rendered in pixels, an image both comfortingly familiar and deeply alien. Against the velvet backdrop of space appeared a luminous cocoon, a teardrop halo of dust and gas glowing faintly around a hidden heart. The shape was comet-like, yet its geometry resisted neat comparison. Textbook diagrams had prepared us for something simple. The cosmos delivered something stranger. The technical readout was stark. The nucleus itself, the solid fragment of rock and ice that anchored this interstellar wanderer, remained stubbornly unresolved. To Hubble's instruments, it was nothing more than a point source buried in its own atmosphere. but the telescope's precision allowed astronomers to constrain its size. No more than 5.6 kilometers across, about 3.5 miles. Smaller than most terrestrial cities, yet this shard of another star system was generating a coma stretching thousands of kilometers in all directions. A pebble with the presence of a world. The artistry of orbital mechanics revealed itself in the photographs. To keep Atlas centered, Hubble tracked the comet's subtle motion against the star field. As a result, the stars themselves were transformed into streaks, luminous scratches drawn across the frame, while Atlas remained steady. Science became art. The effect made the comet appear to speed down a tunnel of light, a lone traveler separating itself from the fixed constellations around it. The image carried symbolism beyond intention, a visitor from elsewhere, moving to its own rhythm. The coma told its own thermodynamic tale, crossing the 4 astronomical unit threshold where water ice begins to sublimate. Atlas had awakened. Dormant for millions of years in interstellar exile, its surface ices now breathed vapor into space. Dust grains, once trapped in frozen lattices, liberated themselves into vacuum, forming a spherical fog around the nucleus. Yet the fog was not uniform. It elongated away from the sun, sculpted by solar radiation and gravitational pull into the archetypal teardrop of a comet. But here, too, Atlas refused to conform. Most comets flaunt prominent anti-solar tails, bright, dramatic fans of dust blown outward. Atlas's tail was puzzlingly shy, barely discernible. Initial analysis suggested it existed, but geometry concealed it from clear view. The angle compressed the tail into near invisibility. It was not until late August, when the Gemini South telescope in Chile captured ultra-deep exposures, that the suspicion became fact. Astronomers' telegram #7363 confirmed it. Atlas did possess the expected tail, but it was faint, thread-like, hidden in plain sight. Dust loss rates added another twist. Hubble measured activity comparable to familiar comets at similar solar distances. On the surface, that was reassuring evidence of behavior consistent with theory. But context changed everything. This was not a fresh solar system comet. This was an object that had endured interstellar radiation for epochs, a body that should have been chemically altered, its volatiles depleted. And yet it shed material like a young comet on its first inner system passage. Atlas was both ancient and fresh, a contradiction in motion. Hubble's resolution, among the sharpest available from Earth orbit, pushed the data as far as possible. It could outline the coma, constrain nucleus size, and trace faint photometric fluctuations, but it could not pierce the veil. No surface detail emerged. No rotation state was pinned down. Atlas remained a mystery, shrouded in its own exhalations. Studying it was like trying to examine a lighthouse bulb while blinded by its beam. The source, hidden, the glow overwhelming. Even within that veil, subtleties appeared. The coma's brightness was not evenly smooth. Slight variations hinted at localized vents on the nucleus, regions more active than others, sending jets of dust into space. To human eyes, it was only mottled haze. To careful analysis, it was a coded message about hidden topography. But without multiple angles or higher resolution instruments, the message remained cryptic, a set of hieroglyphs carved into vapor. Photometric measurements deepened the paradox. Atlas shone brighter than expected for a nucleus of its constrained size. Two possibilities emerged. Perhaps the nucleus was larger than models allowed, or perhaps the surface was unusually reflective, scattering sunlight with efficiency not typical of dark, carbon-rich comets. Neither explanation fit comfortably with known cometary populations. Either way, Atlas was refusing to play by familiar rules. As July turned into August, Hubble chronicled the comet's evolution. The coma expanded, its radius swelling as solar heating intensified. Night after night, the data revealed growth without clarity. The nucleus stayed hidden, a tease of brightness behind a fog of its own making. Every new image confirmed the strangeness without resolving it. Yet for all its limitations, Hubble had achieved something vital. It provided the visual baseline. Atlas was active, comet-like, yet defiant of convention. Its geometry was subtle, its tail understated, its brightness confounding. Here was not an inert shard of debris, but a body with behaviors and signatures that demanded explanation. Hubble had sketched the outlines of a mystery, one that humanity's other great eye would soon attempt to color in. Because the story of Atlas was not to be told in visible light alone. In the infrared, molecules sing, and Webb was listening. On the 6th of August, 2025, the James Webb Space Telescope trained its segmented mirror on the interstellar wanderer, dissecting its light across the spectrum. What it found would shake every assumption built from Hubble's imagery. The chemistry of Atlas, revealed in infrared fingerprints, was unlike anything astronomers had seen. Ratios of carbon dioxide to water that defied logic. Molecular abundances that pointed toward environments our models barely accounted for. If Hubble's gift was paradox in image, Webb's would be paradox in composition. And so, as Hubble's visual data set the stage, the curtain rose on the next act, a lesson in cosmic humility delivered not through shape or brightness, but through chemistry itself. The numbers told a story that bordered on absurd. Carbon dioxide to water, 8-to-1. Not once, not twice, but consistently across multiple Webb spectra. To appreciate how extraordinary this is, we must remember what normal looks like. In almost every comet observed in our solar system, water dominates, by factors of 10, sometimes 100. Even the driest comets rarely show carbon dioxide ratios exceeding 2-to-1, yet here was 3I, flaunting an 8-to-1 ratio as if daring us to explain it. This was not a comet as we knew them. This was something entirely outside the categories we had prepared. But Webb's discovery proved only the overture. Between the 8th of August and 12th, NASA's Wide Field Infrared Surveyor, part of the FEREX mission, joined the campaign. Its data transformed the puzzle into something even stranger. The carbon dioxide emissions weren't confined to the immediate neighborhood of the nucleus. Instead, they ballooned outward, traced to at least 348,000 kilometers, more than 215,000 miles. The largest CO2 coma ever measured around any comet. To visualize it, take the Earth-Moon system, then expand it by half again. That was the ghostly sphere enveloping 3I. The scale was staggering. How could a nucleus only a few kilometers wide produce an atmosphere stretching wider than entire planetary orbits? The physics pointed to processes far more extreme than anything seen in solar system comets. Either the surface was unimaginably active, or something altogether different was happening, something we lacked language to describe. The spectroscopy deepened the paradox. Webb showed CO2 lines burning bright, sharp, and unambiguous. Water, by contrast, was muted, almost absent. So faint that some astronomers wondered whether Atlas contained significant water ice at all. This conflicted with earlier data from NASA's Swift Observatory, which had recorded hydroxyl radicals, the classic byproduct of water photodissociation. Somewhere between ice, vapor, and dissociation, the water trail seemed to have disappeared. SPHEREX, NASA's wide-field infrared mapper, added yet another twist. Its spectral mapping revealed faint absorption bands at 1.5 and 2.1 micrometers, fingerprints of solid water ice. The ice was there, buried in the surface or locked in subsurface layers, but something was stopping it from sublimating efficiently into gas. The surface was hiding its secrets, releasing carbon dioxide with abandon while holding water hostage. The comparisons with earlier interstellar visitors only sharpened the contrast. 2I divided by Borisov, observed in 2019, showed carbon monoxide dominating over water, a chemical profile pointing to formation in the frozen outer reaches of a planetary disk. But CO2 paints a different origin story. Carbon dioxide condenses at warmer temperatures than carbon monoxide, suggesting Atlas formed in a zone intermediate between icy peripheries and water-rich interiors. A region analogous to our solar system's asteroid belt, too warm for water ice, cold enough for carbon dioxide to freeze. If true, Atlas carried samples from environments we had never touched before, planetary nurseries at temperate distances around alien suns. And yet, the sheer scale of the coma complicated that narrative. How could such a modest nucleus sustain such an immense emission cloud? Some researchers suggested fragmentation. Perhaps Atlas was shedding CO2 prospide, rich chunks, small shards drifting away and continuing to sublimate, inflating the coma far beyond what the nucleus alone could explain. Others argued for solar wind amplification, the idea that an existing gas cloud might be stretched and energized by interaction with charged particles, magnifying its apparent size. Neither explanation fit comfortably within conventional comet science. Both stretched the models thin. Timing only heightened the drama. Just as Atlas was approaching solar conjunction, the period when its visibility from Earth would vanish behind the sun's glare, its chemistry revealed itself as utterly alien. We were watching a laboratory from another star system unfold in real time, powered by our sun's heat, but encoding the frozen memory of a world we would never see. The implications rippled outward. If this was typical of interstellar debris, then our models of planetary system chemistry were woefully incomplete. Perhaps CO2-rich bodies were far more common than theory predicted. Perhaps water-dominated comets, so familiar in our solar system, were the exception rather than the rule. Oumuamua, with its bizarre acceleration, and Borisov, with its CO-rich composition, had already hinted at diversity. Atlas, with its extravagant carbon dioxide, made the case undeniable. The galaxy was not delivering a single class of wanderer. It was handing us a spectrum, a chemical menagerie flung between stars. Yet for all its revelations, the data remained incomplete. Each new observation closed one door only to open three more. Was Atlas a one-off anomaly, or the first member of a hidden population? Were we glimpsing exotic chemistry, or simply the tail end of physics we had yet to model properly? The universe seemed determined to dangle answers just out of reach, teasing us with evidence but withholding certainty. As August faded into September, astronomers tightened their grip on every last observation window. They knew time was running out. Soon Atlas would slip behind the sun, taking its secrets with it. For now, it hovered like a question mark carved in vapor, daring us to solve a puzzle written across hundreds of thousands of kilometers of carbon dioxide. The numbers were clear. The meaning was not. Part 4. What we still don't know. 3 months after discovery, with the world's most advanced instruments locked onto 3i, the paradox is sharper than ever. We know too little about too much. Each new observation has illuminated another corner of this interstellar riddle, yet the most basic questions, the ones that could anchor our understanding, remain maddeningly unresolved. The nucleus size epitomizes the dilemma. Hubble's imaging constrains its diameter to somewhere between 320 meters and 5.6 kilometers. That range spans everything from a sports stadium to a small city. This is not a failure of technology, but the inherent limitation of studying an unresolved object veiled in its own halo of dust and vapor. The solid heart could be a compact, bright sphere, or a long, tumbling fragment of darker rock. Without direct resolution, astronomers are sketching guesses inside a fog. Rotation state is no less elusive. Most small bodies in our solar system rotate with periods measurable in hours, producing telltale brightness variations as their irregular shapes turn sunlight toward and away from Earth. But 3i appears eerily steady. Its light curve shows none of the expected periodic flickers. This stability forces uncomfortable alternatives. Either the comet rotates extremely slowly, spins nearly polar relative to Earth, or it possesses a surface so uniform that its rotation leaves no photometric imprint. Each scenario implies a different history. Slow spin could indicate tidal modification during a past encounter. while uniform brightness could mask an unusual surface texture. Water complicates matters further. Early swift observatory detections of hydroxyl radicals, a reliable proxy for water vapor broken apart by solar radiation, suggested substantial water activity. That fit expectations for a comet. But SphereX's infrared mapping set strict upper limits, essentially muting the water story. How can one dataset imply abundant water while another denies it? The explanations range from mundane geometry effects to deeper flaws in how we interpret hydroxyl production in extreme environments. For now, the contradiction remains unresolved. The tail morphology adds to the confusion. Theory demanded an anti-solar tail, dust and gas streaming away under the push of radiation. Yet, for weeks, none appeared. Only in late August did Gemini South finally confirm a faint, thread-like tail extending opposite the Sunday. Why the delay? Theories include unusually large dust grains resisting radiation pressure, or an unfortunate viewing geometry that compressed the tail into invisibility. Either option hints at unusual physical properties. Even more puzzling is the coma's sunward elongation. In several Hubble frames, material appears to drift toward the Sun, not away from it. At first glance, this defies physics. Radiation pressure should always drive particles outward. Later modeling suggested the apparent geometry might be an illusion of perspective, three-dimensional gas flows projected onto two-dimensional images. But astronomers cannot yet rule out that something genuinely exotic is shaping this visitor's activity. Composition remains a frontier of uncertainty. Webb and SphereX have mapped the headline gases CO2 dominating, water suppressed. But what about trace constituents? Sulfur compounds, noble gases, or complex organics could transform our understanding of its origin. Each molecule carries fingerprints of formation, temperature, radiation exposure, and stellar chemistry. Detecting them, however, requires long integration times. Every day, Atlas recedes. Every hour lost to scheduling constraints reduces the sensitivity available for these delicate hunts. The cruelest irony is timing. The period of maximum heating perihelion coincides with solar conjunction, when Atlas is hidden behind the Sun from Earth's perspective. In other words, the climactic moment of activity will occur out of sight. We will glimpse only the after scene, like arriving at a theater after the curtain has already fallen. Speed compounds the challenge. At over 200,000 kilometers per hour, Atlas races across the sky so quickly that even sophisticated tracking systems are strained. For ground-based telescopes, keeping the target centered requires pushing mounts to their limits. For space-based observatories, the scheduling windows shrink as the comet slips from one pointing geometry to another in mere days. Every delay translates into weaker signal-to-noise and lost opportunities. The question of origin hangs over all this uncertainty. We know Atlas is interstellar. Its hyperbolic orbit makes that undeniable. But tracing it back to a specific star system requires exquisite precision in trajectory data precision we lack. Gravitational nudges from planets, solar radiation pressure, and even minute outgassing forces have perturbed its path since entry. Current best estimates place its source within the galaxy's thick disk population, stars that formed 10 to 12 billion years ago when the Milky Way was young. But this is informed speculation, not certainty. Its true birthplace remains hidden in the galactic crowd. Even the driver of its activity is unsettled. Are we witnessing ordinary sublimation of ices, extreme fragmentation events, or something stranger, like electrostatic interactions with the solar wind? The enormous CO2 coma extending hundreds of thousands of kilometers defies simple sublimation models. Fragmentation offers one explanation, exotic surface chemistry another. Both stretch existing comet physics to uncomfortable limits. And so the paradox sharpens. We know enough to appreciate 3I's uniqueness, its speed, its chemistry, its comet-like yet alien behavior. but we lack the answers that would transform curiosity into comprehension. As the object slips toward conjunction, tension builds. Will the December reappearance provide clarity, or will it confirm that some mysteries remain beyond reach? In the end, 3i exemplifies the universe's most maddening habit: to offer visitors that answer questions with more questions. We chase them with billion-dollar instruments, only to find ourselves staring at shadows, squinting at clues, and wondering if the true story is hidden just beyond the edge of perception. The universe, it seems, is particularly fond of leaving us with mysteries disguised as comets. Part 5. What counts as interstellar? In truth, the cosmos doesn't issue passports, but if it did, 3i would surely carry the seal of another star. That claim isn't just poetic metaphor. It is backed by the rigorous grammar of orbital mechanics, where a few stark numbers tell stories of journeys stretching over millions of years. Eccentricity is destiny. Below 1, an object is bound to an elliptical orbit. Equal to 1, it skims a parabolic edge. Greater than 1, its path opens into infinity. For 3i, the value hovers near 1.7, an unambiguous declaration of freedom from the sun's grasp. Even Jupiter, the gravitational heavyweight of our system, can do little more than bend its path slightly. More conclusive still is the parameter known as v infinity, the velocity an object maintains if measured infinitely far from the sunday. For bodies born here, that value is essentially zero. Gravity always ensures their eventual return. But Atlas carries a v infinity of about 25 kilometers per second, nearly the same speed at which Earth itself races around the sunday. That is not the momentum of a local fragment. It is the kinetic fingerprint of a birth environment utterly alien to ours. This rarity is what makes 3i so striking. Consider Atlas, the asteroid terrestrial impact last alert system. 4 robotic telescopes scanning the skies every 2 days, covering millions of patches of stars, cataloguing hundreds of thousands of near-Earth objects. In nearly a decade of relentless observation, only one confirmed interstellar traveler has emerged: Atlas itself. That doesn't mean interstellar space is empty. Theoretical models suggest that every cubic light-year of the galaxy holds thousands of such fragments, flung outward as young planetary systems tear themselves into order. The difficulty is not abundance but detection. They are faint, small, and fast. By the time we notice them, they are often already streaking toward the exit. Only in the era of modern survey science have we had a fighting chance of catching them. Pan-STARRS delivered the first, Oumuamua, in 2017. Catalina added Borisov in 2019. And now, Atlas has given us Atlas. The process of confirmation is rigorous, almost judicial. An initial detection triggers urgent follow-up from telescopes worldwide. Positional measurements refine the orbit. Orbital software tests every possibility, and only when multiple teams independently agree that the object is hyperbolic and not the child of any local reservoir does the International Astronomical Union grant it the coveted I designation. 1i Oumuamua, 2i Borisov, 3i. Each numeral is more than a serial number. It is a verdict returned by a global community that the object is truly from the stars. And soon, the statistics may change. When the Vera Rubin Observatory comes online, its wide-field camera will sweep the southern sky every 3 nights, with a sensitivity unmatched in history. Forecasts suggest it could detect anywhere from 1 to 70 interstellar visitors each year. What was once a miracle may soon become routine. Yet routine does not mean trivial. Every interstellar object is a physical sample couriered across incomprehensible gulfs. Each carries chemical and isotopic signatures locked into its ices and dust from planetary nurseries we will never visit. They are time capsules of other worlds, evidence that our galaxy's diversity is deeper than our current theories admit. The trajectories they follow also mean we only get one chance. Unlike comets bound to the sun, they will never return. All the data we can gather must be harvested during their single, brief passage through our skies. Atlas's credentials as interstellar are therefore beyond dispute. The real mystery lies not in where it comes from, but in what kind of system could create such a wanderer, and why its chemistry is so different from anything we expected. In this, the universe seems to enjoy playing tricks. In less than a decade, we have greeted 3 confirmed guests, each one confounding us in its own way. Oumuamua was the poker-faced stranger. No coma, no tail, just a tumbling shard with a polished glint until it accelerated in defiance of explanation. The anomaly was tiny, 1/10,000th of Earth's gravity, but undeniable, and scientists scrambled to explain it with hydrogen outgassing, reflective radiation pressure, even speculative notions of solar sails. The debate still echoes. Borisov, by contrast, behaved like the model student. A textbook comet, haloed in dust and gas, its chemistry matched expectations and reassured astronomers that most such objects would be ordinary. Then came Atlas, recognizably cometary, yes, but chemically outrageous, with a carbon dioxide to water ratio so extreme it rewrote our assumptions, and a gas cloud so vast it dwarfed planetary orbits. These 3 together make it impossible to dismiss interstellar objects as mere curiosities. They are messengers in matter, fragments of alien environments scattered across the galactic sea. Each is a challenge to our imagination, a reminder that the diversity of planetary systems far exceeds the neat categories we build in textbooks. To call something interstellar is not just a technical label, it is an admission. This rock, this ice, this faint smudge of light in a telescope is not from here. It is driftwood from another shore, evidence of cosmic processes that shaped worlds under alien suns. And standing on our small island of light, we are left to marvel at what stories these silent couriers might yet tell, and at how little we truly know of the ocean they cross. In 2019 came 2I Divided by Borisov, a visitor that at first seemed like a familiar friend, carrying with it the features astronomers expected of a proper comet. Unlike Oumuamua before it, Borisov displayed all the textbook hallmarks: a bright coma, a sweeping tail, and the steady release of water vapor and dust as it drew closer to the Sunday. Yet even this apparently conventional messenger delivered a surprise, its chemistry laced with an unusual abundance of carbon monoxide, far more than in typical solar system comets. The ratio of carbon monoxide to water suggested Borisov had formed in a far colder environment than our own outer solar system, perhaps orbiting a star with a vast disk of ices extending deep into space. If Borisov was the classical comet we had been waiting for, it still carried an exotic fingerprint, one that hinted at planetary nurseries stranger than our own. Now 3I has entered the stage as the 3rd act of this unfolding drama, and once again the script has changed. Where Oumuamua left no gas at all, and Borisov released carbon monoxide in abundance, Atlas is dominated by carbon dioxide. The sequence first, no detectable outgassing, then an excess of carbon monoxide, now a dominance of carbon dioxide, reads almost like a deliberate progression, each arrival showcasing a different environment of formation, as though each visitor carried the signature of a universe all its own. The physical contrasts are equally dramatic. Oumuamua's elongated, tumbling shape resembled a shard of cosmic glass, some 400 meters long but only about 40 meters wide, with a length-to-width ratio so extreme it provoked speculation about artificial origins. Borisov, in contrast, looked comfortingly familiar, a near-spherical nucleus wrapped in a symmetrical coma and sporting a clear anti-solar tail. Atlas sits uneasily between these extremes. Its coma appears compact and spherical, suggesting a solid nucleus rather than a fragmenting shard. But the faint tail that finally became visible in late August is strangely muted, far less flamboyant than Borisov's dramatic plume. The geometry hints at controlled, localized outgassing, more restrained than the wild eruptions usually seen as comets near perihelion. Size estimates add another dimension to the comparison. Oumuamua was small, a cosmic needle barely half a kilometer long at most. Borisov's nucleus measured around half a kilometer across, typical for an average comet. Atlas, by contrast, seems more substantial, with an upper limit of about 5.6 kilometers in diameter, though it may be smaller. Together, the three objects suggest that interstellar debris spans a wide range of scales, from compact shards to city-sized icebergs. Even the ways they were discovered speak to their differences. Oumuamua was detected almost too late, already speeding away from the Sun when Pan-STARRS noticed its unusual trajectory, an accidental catch during a routine asteroid sweep. Borisov was found early, still inbound from the depths of space, affording astronomers months to prepare their observations. Atlas was discovered at a sweet spot, close enough for detailed study but still inbound enough for advanced planning, ensuring a rare opportunity for multi-instrument campaigns across ground and space observatories. Their chemistries point toward three distinct formation zones. Oumuamua's lack of detectable outgassing may indicate a long interstellar journey that stripped away its volatile ices, or perhaps an origin in a particularly dry region of its parent disk. Borisov's carbon monoxide signature points to formation in a cold, outer disk, where such volatile ices remain stable. Atlas's carbon dioxide dominance instead implies an intermediate environment, perhaps at a snowline where water existed as vapor but carbon dioxide could freeze. Each one, in essence, carries a fingerprint of a different nursery of planets, a record of alien chemistry preserved in frozen time. Their behaviors differ just as starkly. Oumuamua displayed a baffling acceleration, tiny but real, as though propelled by forces beyond simple gravity. Hypotheses ranged from outgassing too subtle to observe, to radiation pressure acting on an unusually reflective surface, to more exotic notions involving artificial propulsion. Borisov, in contrast, behaved exactly as the models predicted, its path following gravity and outgassing with reassuring consistency. Atlas so far appears dynamically well behaved, its orbit neatly explained by gravitational physics, yet its massive, extended carbon dioxide coma leaves us grappling with how such a small nucleus could generate such a vast envelope. Survey bias reminds us that much of what we see depends on timing, geometry, and luck. Oumuamua may have once been active, but we caught it too late. Borisov's normal appearance might have looked less conventional if seen from another angle. Atlas's faint tail may reveal more dramatic activity when viewed from the perspective of Mars during its October encounter. Each object carries its own quirks of observation, shaped as much by our vantage point as by its intrinsic nature. Yet taken together, the trio paints a picture of startling diversity. In less than a decade, humanity has seen 3 confirmed interstellar visitors, and not one of them resembles the others. One is a silent, tumbling shard, another, a classical comet with alien chemistry, and now a carbon dioxide enigma, swelling with a gas cloud larger than planetary orbits. If the first 3 samples are this different, what wonders will the next dozen reveal? Each new interstellar object is like a core drilled into a different planetary nursery, carrying chemical fingerprints from worlds we will never visit. They are messengers from the galaxy, fragments of distant systems that together form a mosaic of cosmic diversity. The progression from Oumuamua to Borisov to Atlas feels almost as if the universe is taunting us, challenging every assumption we build. First a comet that isn't, then a comet that is, and now a comet that is but in ways no theory prepared us for. Atlas's muted tail, its sprawling carbon dioxide cloud, and its oddly precise trajectory remind us that the space between stars is far richer and stranger than we once believed. As it approaches its date with solar conjunction, fading into the glare of our sun, we're left with questions that may never be answered. Does its chemistry reflect an environment common to many stars, or is it a rare anomaly? Is its subtle behavior a quirk of geometry, or a sign of processes we've never imagined? What seems clear is this: the cosmos has only begun to reveal its variety. If 3 visitors can defy our expectations so completely, the future promises not just answers, but deeper mysteries waiting to be discovered. And perhaps that is the true gift of these wanderers from other suns. Not certainty, but an unending reminder that the universe is more diverse, more creative, and more unfathomable than we ever dared to dream. Part 6. The Dynamics Puzzles. The universe has a habit of tucking its greatest revelations into the smallest discrepancies, and nowhere is this more striking than in the way interstellar wanderers shift, twist, and glide through the solar system. The tale of 3I is, at its heart, a study of physics in motion, of faint accelerations and delicate forces that may hold the keys to truths far larger than the object itself. We saw the first hints of this mystery with 1I, Oumuamua, in 2017, when it began accelerating away from the Sun in a manner no gravitational model could explain. The effect was vanishingly small, just about 10 micrometers per second squared, a mere 1/10,000th of Earth's surface gravity, but persistent and measurable across weeks of observation. Multiple telescopes confirmed the anomaly, turning what might have been a routine study of a tumbling shard into one of the greatest puzzles in modern astronomy. The acceleration pattern resembled outgassing, the venting of gas from the sunlit side of the body, but no telescope ever caught sight of the expected coma or dust plume. Oumuamua accelerated like a comet but looked like an asteroid, forcing scientists to entertain increasingly unconventional possibilities. Some proposed it was venting hydrogen, so diffuse as to be invisible to our instruments. Others argued that radiation pressure, acting on an unusually reflective surface, might nudge it along. A few even speculated about artificial origins, though such ideas remained well outside mainstream consensus. In contrast, 3I appears, at least for now, to be playing by Newton's rules. Its orbit matches gravitational predictions neatly, following the smooth hyperbolic arc expected of a star-forged comet, making a brief pass through our neighborhood. Yet this apparent normalcy may prove deceptive. The anomalies in Oumuamua's motion only became apparent as it moved away from the Sun after careful measurements accumulated over weeks. Atlas has yet to reach perihelion, and the most revealing data may only emerge during or after its closest approach. What makes the situation even more intriguing is Atlas's chemistry. Where Oumuamua inspired a hydrogen outgassing hypothesis, Atlas flaunts a coma rich in carbon dioxide. These molecules are heavier, easier to detect, and transfer momentum differently. If Atlas begins to deviate from pure gravitational motion, the pattern of its acceleration might tell us whether Oumuamua was a one-off curiosity or a representative of a larger class of volatile-driven interstellar bodies. Geometry complicates matters further. When Hubble observed Atlas, it noted an elongation of the coma seemingly toward the Sun, as though gas were flowing inward rather than outward. This oddity startled researchers until they recalled how three-dimensional flows, when projected into 2 dimensions, can mimic impossible behaviors. Gas jets can curl, spiral, or bend under electromagnetic influences, appearing sunward even when streaming away. The faint anti-solar tail that finally revealed itself in late August confirmed that radiation pressure was indeed sculpting Atlas's coma. Still, the asymmetries hint at a more complex dance of gas, dust, and solar forces than we usually see. The extended carbon dioxide envelope presents perhaps the most dramatic dynamical puzzle. How does a nucleus a few kilometers across generate a gas sphere hundreds of thousands of kilometers wide? Such scale suggests either a nucleus astonishingly active, venting far more vigorously than typical comets, or mechanisms that spread gas production across a much larger volume than the solid body itself. One possibility is fragmentation. Atlas could be a loose cluster of smaller chunks, each outgassing independently. But Hubble's sharp eyes have not revealed the multiple peaks or elongated structures we would expect if this were true. Another possibility lies in the interaction between the escaping molecules and the solar wind. As CO2 is ionized by ultraviolet radiation, it may become entrained in magnetic fields, accelerating outward in ways that magnify the coma far beyond thermal sublimation alone. Atlas's spin state deepens the mystery. Most comets tumble chaotically, their jets acting like tiny thrusters that torque their rotation. Such tumbling usually produces brightness variations in long-term observations. But Atlas's light curve is stubbornly flat, showing no periodic changes. Either it rotates very slowly, we happen to be viewing it almost directly along its spin axis, or its surface is unusually uniform. Each scenario carries distinct implications. Slow rotation could suggest internal cohesion or damping mechanisms. Pole-on viewing a stroke of observational luck, and uniform surface properties a hint at exotic composition. Any of these would set Atlas apart from the norm. Hints of early activity raise further questions. Data from the Transiting Exoplanet Survey satellite, SAS, suggest Atlas may have been active even when it was still beyond Jupiter's orbit, far from the heat that normally triggers sublimation. If confirmed, this would point to volatiles more sensitive than water ice, or to some mechanism independent of solar heating altogether. Could cosmic rays, magnetic fields, or internal processes be driving such early awakening? The answer remains elusive, but it underscores just how unusual this visitor appears to be. As Atlas nears perihelion, the stakes rise. Will it reveal non-gravitational accelerations like those that baffled us with Oumuamua? Will detailed imaging show jets and localized venting, the fingerprints of dynamic processes shaping its vast carbon dioxide cloud? Or will it glide through on a purely gravitational trajectory, challenging us in different, subtler ways? What is clear is that we are witnessing dynamics written across aeons. Atlas's path was set long before Earth even existed, its momentum carried across interstellar gulfs by forces we only dimly perceive. Now, in the brief moment of its solar encounter, those forces are playing out in real time under the scrutiny of our finest instruments. Each photon captured, each spectral line analyzed, represents another clue in a story that began in an alien planetary nursery and will end far beyond the reach of human eyes. The puzzle of 3I is not just about where it came from or what it's made of, but about how matter behaves when set adrift between stars and then caught, however briefly, in the gravity of another sun. And in these faint accelerations, these barely measurable tugs and torques, we may glimpse the deeper physics that governs not only comets but the restless universe itself. Part 7. The Global Watch. Who is observing, when, and how? By the summer of 2025, 3I had become the most intensively monitored interstellar visitor in the history of astronomy. What began as a faint smudge on survey images from Chile quickly evolved into a global scientific campaign, a coordinated choreography of telescopes, spacecraft, and researchers operating as if they were instruments in a symphony of discovery. Every major space agency and observatory, from mountaintop facilities to orbiting satellites, found itself drafted into the effort. The result was nothing less than humanity's first true planetary-scale observation campaign directed at a single cosmic wanderer. NASA's Science Mission Directorate led the formal coordination, establishing a multi-mission framework that pooled resources across divisions normally siloed. The Hubble Space Telescope assumed the role of high-resolution scout, capturing images sharp enough to constrain the size of the nucleus and reveal changes in coma morphology invisible to ground-based instruments. The James Webb Space Telescope became the chemical analyst, deploying its infrared spectrographs to parse trace gases at concentrations down to parts per million. Meanwhile, the Swift Observatory contributed ultraviolet monitoring, watching molecules in the coma shatter under the glare of solar radiation. Each instrument addressed a different slice of the puzzle, and together they provided a multi-wavelength portrait no single platform could achieve. One unexpected star of the campaign was the FAIR-X mission. Originally built to map the infrared sky for cosmology, its wide-field design turned out to be ideal for tracking the vast envelope of carbon dioxide that surrounded the comet. Paired with Webb's ultra-precise spectroscopy, FAIR-X delivered spatial context, not just which gases were present, but how far they extended and how they interacted with solar wind. The synergy between narrow precision and broad coverage became a model for collaborative astronomy. Ground-based observatories, organized through the International Astronomical Union's Rapid Response Network, ensured that 3I never left the global gaze. Gemini North in Hawaii produced the early images showing a compact coma. Its southern twin in Chile delivered deep exposures in late August that finally revealed the faint anti-solar tail. Palomar's next-generation survey contributed steady astrometry, refining orbital parameters with every clear night. In practice, this meant astronomers could track brightness fluctuations almost daily, building light curves that hinted at rotation states and activity cycles. But the most dramatic challenge was written not by technology, but by celestial geometry. Perihelion was set for the 29th of October 2025, a date that placed the comet directly behind the Sun from Earth's perspective. For nearly 2 months, the object would vanish into solar glare, unreachable by any ground-based telescope. The timing was agonizing. Just as the comet should have been most active, its nucleus heated to maximum temperatures, its outgassing at peak intensity, our instruments would be blinded. Astronomers compared it to hearing a symphony's overture and encore while missing the climactic movement. It was a cosmic reminder that even with billion-dollar technology, we remain subject to the geometry of orbits. The blackout spurred creative strategies. Mars, fortuitously positioned, became an auxiliary observatory. On the 3rd of October, 2025, 3I was scheduled to pass within 29 million kilometers of the red planet, closer than some of Mars's own moons. NASA's Mars Reconnaissance Orbiter, with its high-rise camera, was tasked with attempting long-range images. The resolution would not rival Hubble, but even blurred frames would be priceless, providing continuity when Earth-based eyes were blind. Outer solar system spacecraft were also pressed into service. The Psyche mission, en route to a metallic asteroid, would pass within 0.3 astronomical units of 3I in September, raising hopes of opportunistic imaging. ESA's JUICE mission, bound for Jupiter's moons, might catch faint signatures during its November approach. Even OSIRIS-APEX, the extended asteroid sample return mission, was evaluated for potential long-range observations in late 2025. Though none of these missions had been designed with interstellar visitors in mind, their instruments represented rare opportunities to capture perspectives beyond Earth. Meanwhile, radio astronomers joined the hunt. Arrays from the Very Large Array in New Mexico to FAST in China scanned for narrowband emissions that could indicate exotic chemistry or plasma interactions. Planetary radar facilities attempted echo-ranging experiments, bouncing signals off the nucleus in hopes of measuring size and rotation through return delays. Amateur networks also contributed. Small telescopes across suburban backyards logged photometry, building datasets that, though humble, filled observational gaps left by clouds, storms, or scheduling conflicts at larger facilities. Behind the science was an organizational effort that resembled military logistics. Telescope time, normally scheduled years in advance, was being reassigned weekly. Observing slots at flagship observatories were interrupted mid-project to make room for emergency 3I windows. Data pipelines that would ordinarily take months were compressed to days. Teams across continents shared raw files through open archives, allowing spectroscopic data from one telescope to be cross-referenced with imaging from another within hours. The European Space Agency's Planetary Defense Office ensured that the campaign also carried practical value. Though 3I posed no impact risk, the tracking methods, orbital refinements, and coordination exercises mirrored what would be required in a genuine asteroid hazard. Every positional measurement sharpened algorithms that could one day save Earth from a less benign object. The comet thus became both a scientific treasure and a training exercise for planetary protection. As October approached, the sense of urgency grew palpable. The last pre-conjunction nights felt like a countdown to eclipse. Researchers who had spent careers modeling interstellar debris now found themselves racing against orbital mechanics, seizing every hour of data before the blackout. Then, as predicted, the visitor slipped behind the sun's glare, unreachable until early December. The reappearance will mark the beginning of the final act. Emerging in Virgo before dawn, rising toward Leo in the following weeks, 3I will re-enter view, faint but still measurable. By then it will be racing away at more than 150,000 miles per hour, its brightness waning as it fades back into the galactic dark. Post-perihelion studies will be harder, requiring longer exposures and pushing instruments to their limits. But the rewards may be even greater. Observing how the chemistry and activity evolve after solar heating could provide the clearest clues about what lies beneath the surface. Ultimately, the global watch of 3I has represented more than an observational campaign. It has been a planetary-scale experiment in cooperation, proof that the scientific community can mobilize with unprecedented speed and transparency when faced with a fleeting cosmic opportunity. In a time when Earth often struggles with division, the coordination of dozens of agencies and thousands of scientists to study a single object has offered a glimpse of what humanity can achieve when united by curiosity. The true legacy of 3I may not be confined to its chemistry or dynamics, but to the way it transformed a faint moving dot into a shared human endeavor, one that will echo in the protocols, collaborations, and discoveries that follow. Part 8. Could we fly to it? The romantic question meets relentless physics. The idea seems irresistible. Build a spacecraft in record time, light the engines, and chase down 3I before it disappears forever into the night between stars. It has all the elements of a great story: human daring, technological audacity, and a rendezvous with something born in another world. But the romance of pursuit crashes hard against the uncompromising mathematics of orbital mechanics and the stubborn realities of rocket science. The numbers are brutal. By the time astronomers discovered 3I on the 1st of July 2025, it was already hurtling toward the inner solar system at over 200,000 kilometers per hour. Catching up to it would mean not just matching this enormous speed, but also aligning with the precise direction of its three-dimensional velocity vector. In other words, an intercept mission would have to duplicate both magnitude and orientation of a motion scripted by physics across millions of years. That requirement translates into energy demands far beyond what our most powerful rockets can deliver. Space engineers describe such demands in terms of delta V, the change in velocity a spacecraft must achieve. A Mars mission might require around 6 kilometers per second of delta V. A Jupiter flyby might push the requirement to 12, but to intercept 3I directly would require at least 50 kilometers per second, and realistically more. That figure sits firmly in the realm of science fiction, given current chemical propulsion. Even with nuclear thermal engines still untested in space, we would struggle to reach half that number. Matching Atlas's flight would demand a breakthrough in propulsion that we simply do not yet possess. Even if raw thrust were not the problem, time itself is the enemy. By the time a hypothetical intercept probe could be designed, tested, and launched, the target would already be receding. Years would pass while the spacecraft clawed its way along a pursuit trajectory, and by then, 3I would be far beyond reach, accelerating into the interstellar dark. The dream of launching from Earth now, with present-day rockets, is no more than a romantic illusion. Yet impossibility has never stopped engineers from dreaming. If we cannot launch anew, could we instead repurpose spacecraft already in motion through the solar system? several missions suddenly find themselves cast as potential stand-ins for a hurried intercept fleet. NASA's Psyche mission, built to study the metallic asteroid Psyche, will, on the 4th of September 2025, pass within 0.3 astronomical units of 3i. Though Psyche was not designed for comet encounters, it carries cameras and spectrometers that could, in principle, gather valuable data. If mission controllers can choreograph a long-range observation campaign, Psyche may deliver a side benefit: humanity's first spacecraft data on an interstellar visitor, even if the geometry allows only brief glimpses. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, offers another chance. On the 4th of November 2025, right when Earth's telescopes are blinded by solar conjunction, JUICE will cross a position that might allow it to collect useful data. Its advanced imaging suite and spectroscopic instruments could record light curves or chemical signatures, filling in precisely the observational gap that torments astronomers on Earth. Operational constraints and encounter geometry remain difficult, but the possibility illustrates how serendipity often shapes space science. Perhaps the boldest concept involves NASA's veteran Juno spacecraft, which has spent years orbiting Jupiter. A team at the Harvard-Smithsonian Center for Astrophysics has suggested a daring plan. Use Jupiter's enormous gravity as a slingshot to hurl Juno toward a March 2026 flyby of 3i. The maneuver would require an exquisitely timed burn deep in Jupiter's gravity well, converting the planet's orbital momentum into a new trajectory. Pull it off, and Juno could become the first probe to graze an interstellar visitor. Miss the timing by hours, and the opportunity vanishes forever. The plan reads like mission fantasy, and indeed, operational realities make it unlikely. Juno's extended mission is scheduled to end in 2025, its fuel reserves are limited, and reprogramming it for an entirely new trajectory would require approvals that stretch from NASA engineers to congressional oversight. Still, the fact that serious researchers are running the numbers shows how tantalizing the opportunity has become. Mars may offer the most realistic alternative. On the 3rd of October 2025, 3i will pass just 29 million kilometers from the red planet, closer than its moons Phobos and Deimos orbit. The Mars Reconnaissance Orbiter's HiRISE camera, built to image Martian surface details at sub-meter resolution, could be turned outward to capture the passing comet. Even at such distances, the resolution might approach 30 kilometers per pixel, nowhere near Hubble's clarity, but invaluable during the months when Earth-based eyes are blinded. A faint smudge in MRO's field of view would still represent history's first interplanetary vantage on an interstellar object. Other spacecraft have been discussed as well. The OSIRIS-APEX mission, the extended version of the OSIRIS-REx asteroid sample return probe, might in principle contribute imaging late in 2025. Its instruments were designed for close-up asteroid science, but in theory could adapt to study an interstellar visitor. In practice, trajectory constraints and mission schedules make this unlikely. Still, the conversation illustrates a broader point. The astronomy community is scouring every active spacecraft for possible roles in this once-in-a-generation event. Looking ahead, humanity's best hope lies in missions designed from the start for interstellar interception. The European Space Agency's Comet Interceptor, scheduled for launch later this decade, represents exactly that approach. Unlike traditional missions locked to a single target, Comet Interceptor will loiter in a stable orbit, fully fueled and waiting. When a new object, perhaps another interstellar visitor, is detected, the spacecraft can launch toward it within weeks, racing to intercept before the visitor slips away. It is, in effect, a rapid response probe built to exploit opportunities that surveys like Rubin Observatory will surely uncover. The theoretical literature has also exploded since the discovery of 1i, Oumuamua, in 2017. Researchers have modeled everything from solar sails pushed by sunlight to fusion rockets using onboard plasma. From gravitational assist chains leveraging multiple planetary flybys to laser-propelled probes, the numbers are daunting, but not impossible forever. A sustained investment in next-generation propulsion might one day make interstellar intercepts routine rather than impossible. And what would be the payoff? Direct measurements could change our view of cosmic history. Isotopic ratios could reveal which stellar nurseries gave birth to such objects. Mineral structures might encode the chemical conditions of alien disks. Even the surface morphology, whether smooth ice, porous aggregate, or crusted with exotic compounds, would answer questions that remote observations can only hint at. Such data would be the difference between reading a summary and holding the book in your hands. For now, the irony is bitter. Interstellar objects like 3I are the closest thing we have to physical samples of alien planetary systems delivered free of charge by galactic dynamics. And yet they race past too quickly for us to capture. We are like scientists watching priceless specimens slide past a laboratory window close enough to see, impossible to reach. Still, every failed pursuit plants seeds for the future. Each feasibility study, each imaginative trajectory model, each spacecraft repurposing attempt, lays groundwork for the day when the next visitor is discovered. Someday, whether through solar sails, nuclear propulsion, or yet unimagined drives, we will be ready. We may not chase down 3I, but it is teaching us how to prepare for its successors. In that sense, the romantic question is not wasted. It is the spark behind serious research, the dream that fuels innovation. Could we fly to it? Not today, but one day, when another cosmic messenger sweeps into our neighborhood, the answer might finally be yes. Part 9. Why carbon dioxide? Natural explanations on the table. The chemistry of 3I reads like a riddle written in invisible ink, revealed only through the spectral lines of telescopes. Unlike the comets we know, this interstellar traveler is dominated by carbon dioxide in ratios that overturn decades of expectations. Before we leap to the speculative frontier alien technology, exotic physics, the discipline of science demands we exhaust every natural explanation, and as it turns out, the universe offers many plausible pathways to produce exactly the strange chemistry we see. One elegant possibility is the carbon dioxide snowline hypothesis. In protoplanetary disks, temperature gradients establish chemical borders as sharp as climate zones on Earth. Far from a star, water ice condenses in abundance. Closer in, volatile species condense in their own narrow bands. Ammonia, methane, carbon monoxide, carbon dioxide. Each has a freezing point that fixes its snowline. If 3I formed just inside the water snowline but beyond the CO2 snowline, it would naturally accumulate carbon dioxide ice while being poor in water. This chemical sweet spot is analogous to the asteroid belt in our solar system, warm enough for water to remain vapor, yet cool enough for CO2 to condense into solids. Such an environment would produce precisely what Webb and SphareX see, an object unusually rich in carbon dioxide, yet reluctant to give up its water. The snowline explanation is tidy, but stellar diversity complicates the story. Disks around different stars create entirely different architectures. Around low-mass red dwarfs, the CO2 snowline might lie closer in, broadening the zone where CO2 dominates. Around luminous stars, radiation reshapes disk chemistry, allowing CO2 to form through alternate pathways. In other words, 3I may not be exotic at all, it may simply carry the fingerprint of its natal star, born in conditions our solar system never experienced. Another candidate is radiation processing, the inexorable chemistry of deep time. Interstellar space is not empty. It is soaked in high-energy particles that bombard any traveler. Over millions or billions of years, cosmic rays can split molecular bonds, rearrange atoms, and build new compounds out of simpler ones. Radiolysis is a kind of chemistry that ignores the laboratory, working instead across geological epochs. In this cosmic laboratory, Water ice is fragile. Bombard it long enough, and it fragments, either escaping entirely or reassembling into other compounds. Carbon dioxide, by contrast, is more resistant. Some models even suggest that cosmic rays can manufacture CO2 by breaking down organic ices and recombining their fragments. If this is correct, then the reddish hues observed in 3I's spectrum, hints of radiation-darkened tholins, are evidence of this long interstellar alchemy. Perhaps 3I is not unusual at all. Perhaps all ancient travelers gradually transmute into CO2-rich bodies under the ceaseless hammer of radiation. Then comes the insulating crust hypothesis, an explanation born from laboratory studies of ices and organics. As comets age, repeated heating and cooling can weld a crust of organic-rich material to their surfaces. This crust acts like a thermal blanket, tough enough to trap water vapor beneath, yet riddled with cracks that allow more volatile gases to escape. Since CO2 sublimates at lower temperatures than water, it can slip through thin seams, even while water remains locked below. In this model, 3I might contain abundant water ice, but its gas phase is choked off by a hardened rind. The Webb detection of copious CO2 gas paired with Sphere X's evidence for solid phase water ice fits neatly into this framework. The water is there, hidden, insulated, waiting for a deeper heat pulse to free it. Another possibility turns the question of structure inside out, the icy fragments hypothesis. Instead of a single monolithic nucleus, what if 3I is a loose assemblage of carbon dioxide-rich chunks, weakly held together by gravity and cohesion? Such a rubble pile would act like a distributed source of gas. As sunlight warms the clump, fragments separate and sublimate independently, creating the vast CO2 coma we observe. This would explain why the coma extends hundreds of thousands of kilometers, yet the nucleus remains unresolved. It would also clarify why brightness remains relatively stable despite such vigorous activity. The gas is being produced by many small contributors, not a single central jet. The thermodynamics of temperature dependence provide yet another natural key. At the distances where 3I currently travels between 2.5 and 3.5 astronomical units, water sublimation is inefficient. Carbon dioxide, however, remains highly volatile at these temperatures. Physics alone predicts CO2 should dominate. As perihelion approaches, the nucleus will warm further. If the current ratios arise from temperature effects rather than composition, then post-perihelion observations should reveal an upsurge in water vapor. The CO2 divided by H2O ratio should evolve predictably, tracking sublimation curves tested in laboratories. This prediction is not speculation. It is a falsifiable experiment the cosmos itself is running for us in real time. Even the grain size of dust released offers clues. The anti-solar tail of 3I, barely perceptible in August imaging, hints at larger dust particles than typical comets produce. Radiation pressure sweeps fine dust into brilliant tails, but heavy grains resist, lingering near the nucleus. CO2-driven sublimation may preferentially loft larger aggregates or alter their charge states, producing the muted morphology we see. Again, the physics is natural, the evidence testable. Taken together, these explanations remind us that the extraordinary may be built from ordinary parts. A snowline birth environment, millions of years of radiation chemistry, an insulating crust, a rubble pile nucleus, volatile dependent outgassing, and unique grain dynamics. Each mechanism is known. Each could, alone or in combination, sculpt the strange face of 3I. None requires alien engineering or new physics. And yet, abundance becomes its own problem. With so many explanations on the table, which is the right one? Are we seeing the signature of formation, or the scars of interstellar travel? Are we witnessing a unique body, or a representative of a class we have simply never seen before? The data are not yet decisive, but science thrives on such uncertainty, because every natural explanation carries implications. If snowline chemistry dominates, we are sampling an intermediate region of a protoplanetary disk for the first time. If radiation processing is responsible, then interstellar space itself is shaping the composition of galactic debris. If an insulating crust or rubble pile structure holds the answer, then cometary physics may be far more varied than we thought. The lesson of 3I is not that the universe is inexplicable, but that its explanations are layered, contingent, and sometimes indistinguishable with limited data. We may never pin down a single cause, but every candidate pathway teaches us something about the cosmos. The real miracle is that a lump of ice and rock, no larger than a small city, can carry chemical truths from another star system across billions of years, only to give us a few months of study before it vanishes again into the dark. Part 10. Where could it have come from? Tracing 3I back to its stellar birthplace is like reconstructing a crime scene scattered across light years and eons. The trail of evidence is faint, encoded not in fingerprints or DNA but in orbital mechanics, kinematic vectors, and chemical signatures. Every number we measure its speed, its angle of approach, its composition serves as a clue to an origin story, written long before Earth was even a possibility. Yet, as in any cosmic investigation, the closer we look, the more the answers blur into probabilities rather than certainties. The leading hypothesis today is the thick disk origin. The Milky Way is not a uniform system, but a layered history of stellar populations. The thin disk, where our Sun resides, contains relatively young stars, rich in metals, astronomical shorthand for elements heavier than helium. These stars were born into a galaxy already enriched by countless supernovae. Above and below this thin disk lies the thick disk, an older population formed when the galaxy was turbulent and half its present age. Beyond both stretches the stellar halo, a vast sphere of ancient, metal-poor stars, relics of the galaxy's earliest epochs. Each of these populations carries distinct kinematic fingerprints, moving in characteristic orbits that reflect the gravitational environment of their birth. The motion of 3I points unmistakably toward the thick disk. Its velocity vector, relative to the local standard of rest, roughly 25 kilometers per second, is consistent with objects formed during the era astronomers call cosmic noon, 8 to 12 billion years ago, when the universe itself was young and galaxies like ours were producing stars at ferocious rates. If this origin is correct, 3I is not simply a piece of frozen debris. It is a survivor from a time when Earth, the Sun, even the spiral arms of our galaxy, did not yet exist. A thick disk birthplace carries profound implications. Stars of that era formed from gas clouds that were chemically poorer than those of today. Lower metallicity would have altered the composition of their protoplanetary disks, perhaps tilting the balance toward carbon-rich compounds rather than oxygen-dominated ices. Such a shift could naturally explain the carbon dioxide dominance observed in 3I. Its chemistry may thus be a direct fingerprint of planetary nurseries operating under conditions very different from our own. But identifying a stellar population is not the same as naming a parent star. Any object wandering the galaxy for billions of years undergoes countless gravitational perturbations. Passing stars, molecular clouds, even the tidal forces of the Milky Way itself can nudge trajectories. Over millions of encounters, the original orbital information is smeared away, like ink bleeding across wet paper. By the time 3I reached our telescopes, the precise identity of its home system had long since been erased. What we can say is statistical. This is likely thick disk debris, ejected during the violent youth of the galaxy. The mechanism of ejection is its own story of cosmic violence. Planetary systems are not peaceful cradles. They are arenas of scattering and collision. Giant planets, through gravitational kicks, fling smaller bodies outward. Some are captured into distant reservoirs like the Oort cloud. Others are hurled across the escape threshold, set loose as interstellar wanderers. Close stellar flybys during the early clustering phase of star birth can have the same effect. stripping outer debris belts wholesale and sending their fragments on hyperbolic journeys. 3I is one of these survivors, selected by physics itself. Only objects of certain sizes, structures, and compositions can withstand both the violent ejection and the million-year exile that follows. Every interstellar object we detect is, in effect, a curated sample from this survival bias. The 3 confirmed visitors illustrate how incomplete our sampling remains. Oumuamua, dry and accelerating. Borisov, a textbook comet laced with carbon monoxide. Atlas, a carbon dioxide enigma. Are these true representatives of interstellar diversity, or merely the oddities that our current instruments can detect? Detection biases loom large. Wide-field surveys preferentially find bright, active comets or those crossing geometries favorable to Earth's sky. Countless others, dark, small, or approaching from unfriendly angles, slip past unseen. In this sense, our picture of interstellar debris is like trying to infer the shape of an iceberg from the 3 shards that happen to float near the ship. Chemistry offers a second line of inquiry. The dominance of carbon dioxide implies formation at temperatures where water would not condense, but CO2 could freeze. That requires very particular zones in protoplanetary disks, regions intermediate between the cold outer nebula and the warmer inner regions. If true, Atlas is a fossil from that narrow annulus of a long-dissolved disk. Yet radiation processing during its interstellar journey muddies the picture. Cosmic rays may have altered the ratios, destroying water or generating CO2 from organic ices. The birth chemistry is inseparably entangled with the travel chemistry. In principle, isotopic ratios could break this degeneracy. Different stellar environments produce distinct isotopic signatures, ratios of carbon 1,2 to carbon 1,3, oxygen 1,6 to oxygen 1,8, that act like chemical passports. If we could measure such ratios in 3I, we might pin down not just its population of origin, but the specific metallicity, age, and even stellar type of its home system. Unfortunately, the object is faint, its light diffused through a vast coma, and isotopic spectroscopy at such distances pushes even Webb to its limits. For now, the passport remains illegible. The galactic context places further boundaries on speculation. Some early media reports leapt to claims of an extragalactic origin, suggesting that Atlas might hail from another galaxy altogether. The mathematics, however, are unforgiving. To cross intergalactic distances while retaining the measured velocity vector is implausible. The kinematic data place Atlas firmly within the gravitational framework of the Milky Way. The thick disk hypothesis is not just the simplest explanation, it is the only one consistent with orbital mechanics. What does this mean in practice? It means 3I is older than Earth, older than the Sun, perhaps older than the spiral structure of our galaxy itself. It has witnessed supernovae detonate, star clusters dissolve, and spiral arms shear past one another. It has drifted through environments we can only model in theory, carrying with it the scars of radiation and the memory of conditions long vanished. To study it is to perform archaeology on galactic scales, reading the story of planetary formation written into a fragment of frozen carbon and dust. The December reappearance, when Atlas emerges from solar conjunction, may sharpen the picture. If water emission rises as models predict, the chemistry may align with conventional thermodynamics, pointing to a familiar snowline origin. If the CO2 dominance persists stubbornly, then we may be forced to consider more radical interpretations, formation around unusual stars, or post-formation processing that defies our current frameworks. Either way, every spectrum we collect is a data point in a story far larger than one comet. The coming decade will change the game. The Vera Rubin Observatory's legacy survey of space and time promises to detect dozens of interstellar visitors every year, transforming anecdote into statistics. With hundreds of samples, we can begin to trace chemical distributions, orbital populations, and survival rates. Patterns will emerge where now we see only anomalies. Perhaps then, we will finally answer the question of whether Atlas is unique or typical, aberration or archetype. For now, 3I is best understood as a time capsule, a fragment ejected billions of years ago, wandering ever since, altered but not erased by its journey. Its origin may never be narrowed to a single star, but in a sense that hardly matters. It carries with it the story of an entire population, a galactic epoch, a phase of cosmic history when the raw materials of planets were first assembling. To hold that story in the beams of our telescopes, even for a fleeting season, is to touch the deep past of the Milky Way. And when Atlas vanishes back into the dark, it will leave behind not silence but a reminder. Our galaxy is filled with countless others, still waiting to be found. Part 11. The Avi Loeb Chapter. Open, minded, and controversial. In the landscape of modern astronomy, few names provoke as much discussion or division as Avi Loeb. A Harvard astrophysicist, prolific writer, and unapologetic contrarian, Loeb has built his reputation on challenging orthodoxy. For his admirers, he is the rare scientist willing to articulate questions others dismiss too quickly. For his critics, he blurs the line between disciplined inquiry and speculative publicity. The arrival of 3I has provided him with another stage, and his engagement with this enigmatic visitor showcases both the strengths and controversies that have defined his career. Loeb's involvement began almost immediately after the July 2025 discovery. Within days, he had published his first essay, dissecting the orbital parameters, brightness, and coma morphology of the new interstellar object. What marked his work was not only the speed of his commentary, but the precision with which he tracked emerging anomalies. His 27th of August analysis, for instance, claimed that careful image stacking revealed a faint anti-solar tail that other teams had overlooked. Days later, Astronomer's Telegram 17,363 confirmed the presence of this subtle tail, vindicating Loeb's assertion that the object was not entirely spherical, but releasing dust in a direction consistent with solar radiation pressure. But Loeb's interpretations rarely stop at confirming consensus. His size estimates quickly stirred debate. Using scattering models and brightness assumptions, he proposed that the nucleus could be several tens of kilometers across, far larger than Hubble's strict upper limit of 5.6 kilometers. Such a discrepancy carries enormous consequences. If Loeb is wrong, it highlights flaws in his modeling assumptions. If he is right, then Atlas may possess surface properties or albedo values unlike anything we've catalogued, raising questions about its material composition and even its fundamental nature. The FEREX infrared mapping data provided a second pillar for Loeb's commentary. He emphasized the scale of the carbon dioxide coma, stretching hundreds of thousands of kilometers, a feature difficult to reconcile with a nucleus so small. For Loeb, the puzzle lay in the physics of outgassing. How could a body only a few kilometers across sustain such an immense envelope of gas? Traditional models, he argued, would predict weaker, shorter-lived activity. Unless Atlas is fragmenting, or unless its surface has unusually active patches, the observed coma suggests processes beyond ordinary sublimation. Loeb's interpretation of the water controversy illustrated his style of synthesis. Early swift observations suggested significant water vapor, inferred from hydroxyl radicals, but SphereX mapping later failed to detect corresponding water lines. Where some commentators saw contradiction, Loeb proposed integration. Perhaps the water exists beneath insulating crusts, trapped below layers of refractory material, while carbon dioxide, more volatile at these distances, escapes freely. Thus, both observations could be correct, pointing to stratified composition rather than error. Where his commentary becomes provocative and inevitably controversial is in his willingness to raise what he calls technological hypotheses. Drawing on the unresolved acceleration anomaly of 1I Oumuamua, Loeb has argued that natural explanations may not be sufficient to account for Atlas's extended carbon dioxide coma, unusual reflectivity, and curious geometry. He emphasizes that these ideas are not conclusions but testable possibilities. Among them is the self-luminosity hypothesis, the suggestion that Atlas might possess internal energy sources, radioactive decay, electrical phenomena, or even engineered mechanisms that maintain activity levels without requiring purely solar heating. Such ideas stretch conventional comet physics but cannot yet be ruled out by existing data. His trajectory analysis adds further fuel to debate. Loeb has noted that 3I's path through the solar system seems oddly optimized for observation from Earth. Its perihelion occurs when it is hidden behind the Sun, denying us direct viewing of its most active phase, but its pre- and post-conjunction geometry provides unusually favorable alignment for space telescopes. Coincidence, most say. But Loeb asks whether coincidences that maximize scientific observability should at least be tested against the hypothesis of intentional navigation. Few astronomers are willing to entertain such speculation, but Loeb insists that refusing to consider it is more dangerous than considering and ruling it out. Beyond theory, Loeb has championed practical proposals. Working with mission planners, he co-authored studies outlining how NASA's Juno spacecraft could, in principle, be redirected using a gravity assist from Jupiter to intercept Atlas in 2026. The trajectory analysis is intricate, requiring precisely timed burns deep within Jupiter's gravity well. Fuel constraints and mission lifetime issues make it unlikely, but Loeb's advocacy underscores his conviction that we should seize every chance to study interstellar visitors up close. He has argued that missing such opportunities is akin to turning away samples hand-delivered from another world. Yet even Loeb acknowledges the speculative character of his more daring claims. His essays almost always frame them in conditional terms. If conventional explanations fail, then alternatives must be considered. The problem, as Loeb himself admits, is timing. Interstellar objects race through the solar system in months, not decades, leaving little opportunity for decisive testing. With Atlas, the window for resolving these puzzles is already closing. The media, predictably, has latched on to his more provocative language, often stripping away his caveats. Headlines trumpet Harvard astronomer says alien technology possible, ignoring the careful scaffolding of conditional logic and alternative explanations. To many in the field, this kind of coverage distorts the scientific process, reducing nuanced hypothesis testing into sound bites that fuel conspiracy theories. But Loeb himself remains undeterred. He argues that science has always advanced by considering the improbable, from pulsars once nicknamed LGM, little green men, to dark energy that defies all classical physics. In his view, refusing to discuss technological hypotheses only impoverishes the scientific discourse. Critics counter that his approach risks undermining public trust in astronomy by overemphasizing low-probability ideas. They note that extraordinary claims require extraordinary evidence, and that presenting alien technology as one hypothesis among many risks granting it undue legitimacy. But even his critics concede that Loeb's insistence on open-mindedness has spurred the community to sharpen its models, clarify its assumptions, and propose new tests. The debate itself is productive, even when the conclusions remain contested. Loeb has proposed concrete observational protocols that could discriminate between natural and artificial scenarios. High-cadence photometry might reveal whether brightness fluctuations are consistent with reflective surfaces rather than random outgassing. Spectroscopy could search for narrow emission lines suggestive of engineered processes. Radar and radio searches could detect coherent signals. And, of course, close spacecraft encounters could provide definitive ground truth. His point is not that Atlas is technological, but that if we fail to design tests, we may never know. This philosophy reflects Loeb's broader outlook on science, that progress comes not from protecting consensus, but from interrogating anomalies. He is fond of pointing out that almost every transformative discovery, quasars, pulsars, gravitational waves, began as data that didn't fit the models of the time. Atlas, with its baffling chemistry and ambiguous morphology, fits squarely into that tradition. Whether the explanations prove mundane or extraordinary is less important than the rigor of the process used to find out. As solar conjunction approaches, and with it the temporary blackout of Earth-based observations, Loeb's urgency has grown. He has called for rapid publication of all available data, for open collaboration across national and institutional lines, and for a willingness to allocate telescope time at unprecedented scales. The object is fleeting, he argues. Hesitation is itself a kind of decision, one that may cost us the chance to learn. In the end, the Avi Loeb chapter of the 3I story may be remembered less for specific hypotheses and more for what it revealed about the culture of science. His presence forces uncomfortable but necessary questions. How open should science be to radical possibilities? How much risk of embarrassment is acceptable in the pursuit of knowledge? And what responsibilities do scientists bear in communicating uncertainties to a public eager for definitive answers? For now, 3I remains what it always was, a puzzle written in gas, ice, and motion, slipping past us on its way back to the stars. Loeb's contributions remind us that puzzles are not solved by consensus alone. They require curiosity, sharp enough to cut through convention, skepticism strong enough to test every idea, and imagination broad enough to consider even those possibilities we find unsettling. Whether his predictions prove right or wrong, his insistence on open inquiry ensures that 3I will not pass unexamined, and that, in itself, is a kind of triumph. Part 12. What could confirm or falsify theories next? The story of 3I is about to enter its most decisive chapter. As the object slips behind the Sun during solar conjunction, astronomers face a forced pause, a cosmic intermission dictated by geometry rather than choice. For nearly 2 months, the most mysterious interstellar visitor yet discovered will be invisible to every telescope near Earth. But when it re-emerges in December, the stage will be set for one of the most intensive global observation campaigns ever attempted in planetary science. The months that follow will represent not only a race against time, but a trial by evidence. Every theory about its chemistry, its structure, its origins, and even its possible artificiality will stand before the jury of observational reality. The first and most critical test will come from spectroscopy. If 3I truly obeys the rules of natural sublimation, then its chemistry should evolve in predictable ways as it retreats from perihelion. The peak heating of late October will have penetrated deeper into its crust, breaking through any insulating layers and releasing volatiles that had remained locked away. In that case, December and January spectra should reveal stronger water emissions than those observed during the approach. Such a shift would vindicate the idea that water was always present, simply trapped below a crust that preferentially allowed carbon dioxide to escape. But if the carbon dioxide dominance persists with little change, it would suggest something far stranger. Either a genuinely water-poor composition, unlike any comet we have seen, or physical processes that maintain a chemical imbalance regardless of temperature. Such persistence would strain conventional cometry models and invite more radical interpretations. Brightness monitoring will provide another line of evidence. Most active comets reveal their rotation through periodic variations in luminosity, as sunlit jets and darkened regions rotate in and out of view. The absence of such variability in 3I has already puzzled researchers. Post-perihelion monitoring will extend the record. If the brightness curve remains flat, astronomers may be forced to conclude that either the rotation axis is aligned in a peculiar way relative to Earth, or the surface is unusually uniform. But if new fluctuations emerge, they will offer direct clues to rotation state, jet structure, and internal dynamics. More provocatively, Any brightness variations inconsistent with solar heating patterns, suggesting controlled orientation or even non-thermal illumination, would be nearly impossible to explain through natural means. High-resolution imaging will complement spectroscopy and photometry. Hubble and the largest ground-based observatories are scheduled to track the development of the coma and tail as Atlas moves away from the Sunday. If it behaves like a conventional comet, the dust tail should lengthen and become more defined, pointing steadily away from the Sun under the influence of radiation pressure. The rate of expansion, the density profile, and the alignment should match textbook models. Any deviations, tails that kink, morph, or resist solar alignment would hint at processes we do not yet understand. Mars will provide an extraordinary vantage point during Earth's observational blackout. On the 3rd of October 2025, Atlas will pass just 29 million kilometers from the red planet. If the Mars Reconnaissance Orbiter's high-rise camera can capture images, even at modest resolution, they will offer crucial insights into coma geometry during the peak of thermal stress. The different line of sight could reveal asymmetries invisible from Earth, helping to distinguish between apparent illusions and genuine physical anomalies. Spacecraft elsewhere in the solar system may contribute in surprising ways. NASA's Psyche mission will pass within 0.3 astronomical units of Atlas in September, potentially capturing imaging or spectral data with its onboard instruments. ESA's JUICE spacecraft may also be in a position to observe in November, during Earth's blackout period. Even the OSIRIS-APEX mission, designed for asteroid science, is being considered for opportunistic observations. None of these spacecraft were built for interstellar comet encounters, but each could provide unique datasets impossible to acquire from Earth. The James Webb Space Telescope remains central to the campaign. Its infrared sensitivity is unmatched, and its ability to detect trace organics, isotopic ratios, and thermal distributions could settle debates about formation zones and evolutionary history. If Webb finds isotopic ratios consistent with early galactic material, the thick disk origin hypothesis would gain strong support. On the other hand, isotopic anomalies might point to exotic processing during interstellar transit, or perhaps even mechanisms beyond natural chemistry. Meanwhile, SPHEREx will continue wide-field mapping of the carbon dioxide cloud, testing whether its scale grows, shrinks, or remains constant. A stable coma of such enormous size, regardless of distance from the Sun, would demand explanations well beyond standard sublimation physics. Astrometry, the careful measurement of position against background stars, will play a subtler but no less decisive role. For Oumuamua, it was tiny but measurable non-gravitational accelerations that ignited controversy. For 3I, the precision tracking of its motion will reveal whether carbon dioxide outgassing produces detectable deviations from a purely gravitational orbit. If the trajectory holds smooth and clean, natural explanations will stand unchallenged. But if accelerations emerge that cannot be reconciled with sublimation models, the door will open once again to exotic physics or, in the most speculative interpretations, technological hypotheses. The power of the upcoming campaign lies in its convergence. Spectroscopy, photometry, imaging, spacecraft flybys, and astrometry will provide overlapping, cross-checking datasets. Each hypothesis, whether conventional or radical, makes not only individual predictions, but correlated ones. Natural cometary physics predicts a rising water signature after perihelion, tail growth that matches solar geometry, rotational modulation of brightness, and acceleration patterns aligned with gas production. Technological or exotic hypotheses predict correlations that differ, persistence of anomalous ratios, non-standard tail geometries, brightness changes unrelated to solar heating, or accelerations decoupled from gas emission. By March 2026, the sum of these observations should allow astronomers to choose between explanations with far greater confidence than is possible today. Yet the stakes are larger than this single object. The campaign represents humanity's responsibility to wring as much knowledge as possible from a fleeting opportunity. After March, Atlas will fade into the darkness, its secrets carried once more into the void between stars. No spacecraft will catch it, no telescope will see it again. The lessons must be learned now or not at all. This, ultimately, is the paradox of interstellar visitors. They are priceless messengers from other systems, each carrying clues about planetary birth and galactic history, but they pass quickly, teasing us with mysteries that can only be solved under unforgiving time pressure. The December-March window will decide whether 3i leaves behind clarity or only deeper questions. Perhaps the greatest gift of this campaign is not the promise of definitive answers, but the discipline it demands. It forces scientists to define what counts as confirmation, what would falsify a theory, and what lines of evidence must converge before we call something understood. In that sense, 3i is more than an interstellar comet. It is a mirror, reflecting our own scientific method back at us, testing whether our curiosity, rigor, and imagination are equal to the cosmic puzzles we claim to seek. The universe has delivered 3i to our doorstep. Whether we meet this visitor with explanations grounded in natural law, or leave the encounter with mysteries unresolved, depends not on what the comet is, but on how we choose to observe it. The story of 3i is not just about a single interstellar traveler flashing briefly through our solar system. It is the beginning of a new chapter in astronomy, a signal that the space between stars is not an empty void but a realm populated by wandering worlds, fragments of shattered planets, and icy debris carrying chemical stories from places we may never visit. Each interstellar object is both a puzzle and a promise, a fleeting mystery that strains our current models, and a tantalizing glimpse of discoveries yet to come. The arrival of 3i shows us that we are no longer passive bystanders. We are building the tools, the frameworks, and the philosophy required to study these messengers systematically rather than episodically. At the heart of this transformation lies the Vera C. Rubin Observatory, poised to change everything we know about interstellar populations. Scheduled for full operations in 2025, Rubin is more than a telescope. It is a cosmic census machine. Its 8.4-meter mirror and vast 3.2 gigapixel camera will map the southern sky every 3 nights, producing a torrent of data unmatched in astronomical history. Theoretical models suggest that Rubin could detect anywhere from a handful to as many as 70 interstellar visitors each year. That range remains uncertain because we simply do not know how abundant such objects truly are. But even a modest detection rate will transform the field from one of anecdote to one of statistics. Up to now, our knowledge has been based on 3 singular cases: Oumuamua's enigmatic acceleration, Borisov's cometary display with its excess carbon monoxide, and Atlas's sprawling carbon dioxide cloud. They are like 3 cryptic runes carved into the fabric of astronomy, too few to form a language. Rubin will provide hundreds, perhaps thousands, of such runes, enough to reveal patterns, correlations, and population trends. With statistical power comes the ability to ask new questions. What kinds of star systems produce debris rich in carbon monoxide versus carbon dioxide? How do ejection processes shape size distributions? How long can icy bodies survive radiation before their chemistry is altered beyond recognition? For the first time, we will have enough samples to test these questions with rigor rather than speculation. Preparedness will be just as important as discovery. The European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, represents humanity's first deliberate attempt to meet such a traveler on its own terms. Rather than launching toward a pre-selected target, Comet Interceptor will wait at the gravitationally stable Earth-Sunday L2 point, a sentinel in deep space. From there, it can spring into action within weeks or months, redirecting itself toward the next interstellar visitor. The design acknowledges the cruel reality. By the time we discover such objects, They are already moving too quickly for missions launched after detection to catch them. If we want to meet them up close, we must be waiting in ambush. The spacecraft will carry cameras to resolve nuclei and jets, spectrometers to parse chemistry in fleeting flybys, and dust analyzers to capture and examine fragments of alien material. It is a machine built for speed and surprise, a reminder that readiness is the new currency in interstellar exploration. The framework being developed for interstellar visitors already pays dividends beyond curiosity. The same wide-field surveys that reveal cosmic nomads also guard Earth from potentially hazardous asteroids. The orbital calculation tools, multi-observatory coordination protocols, and rapid response telescope scheduling pioneered for 3I will sharpen our planetary defense capabilities. In this way, the pursuit of knowledge and the protection of our world become intertwined. A comet from another star system might never threaten Earth, but the systems built to study it could one day save us from a homegrown catastrophe. Public engagement will remain both opportunity and challenge. Every interstellar discovery ignites speculation about alien origins. The story of 3I proved how quickly data can be overwhelmed by narratives of invasion or conspiracy. Yet, it also showed the power of transparency. By releasing data from Hubble, Webb, SphereX, and ground-based observatories into public archives, scientists turned potential rumor into shared investigation. The lesson is clear. Immediate communication that distinguishes between what we know, what we suspect, and what we merely imagine is essential if we are to maintain public trust in the age of interstellar messengers. The collaborative framework pioneered during 3I may be its most enduring legacy. Traditionally, astronomy has relied on carefully planned observing programs scheduled years in advance. Interstellar visitors laugh at such timetables. They demand improvisation, redirection, and cooperation on a global scale. With Atlas, we saw emergency time allocations at major observatories, real-time integration of data across wavelengths, and unprecedented partnerships between academic groups, industry, and citizen scientists. That culture shift from competitive proposals to collaborative urgency may prove as revolutionary as any single measurement. The theoretical landscape is also expanding. Oumuamua forced us to confront the possibility of exotic physics or artificial structures. Borisov reaffirmed the cometary paradigm, but with chemical twists. Atlas added carbon dioxide dominance to the list of surprises. Together they reveal that planetary formation across the galaxy is far more diverse than we imagined. Some systems may favor volatile rich environments that produce comets saturated with CO or CO2. Others may yield barren, rocky fragments. Each visitor is a sample from a laboratory we cannot otherwise enter. The disks around alien stars. Beyond chemistry and physics, the implications touch on philosophy and even biology. If the diversity seen in just 3 objects is representative, then the galaxy contains a vast library of recipes for making planets and perhaps life. Some recipes may produce fertile environments where biology can thrive. Others may yield sterile deserts. Studying interstellar debris is therefore not merely about rocks and ices, but about mapping the possibility space for life itself. The technological demands of chasing such fast, faint targets drive innovation across fields. More sensitive spectrometers, faster image processing, autonomous navigation software, and improved orbital mechanics codes. Each incremental improvement prepares us for the next visitor, but also strengthens astronomy as a whole. From near-Earth asteroid tracking to exoplanet atmosphere studies, international cooperation has proven indispensable. No single nation, agency, or telescope can own an interstellar visitor. The cosmos delivers them to all of humanity, and humanity must respond collectively. During Atlas, we saw US, European, Asian, and South American facilities working in harmony, sharing data almost in real time. This spirit of collaboration will be essential when the next, perhaps even more enigmatic, traveler appears. Education, too, is changing. Students are no longer confined to learning planetary science through Earth, Mars, or Jupiter's moons. They are analyzing real data from objects born around other stars. The case studies of Oumuamua, Borisov, and Atlas are already reshaping textbooks, providing tangible examples that planetary environments across the galaxy follow rules both familiar and strange. Ultimately, the most profound lesson of 3i may be perspective. These objects remind us that our solar system is not an isolated island. Material is constantly exchanged across the galaxy, bridging vast distances of time and space. Each fragment carries the memory of its birthplace, chemical whispers from stars long gone, frozen relics of processes that occurred billions of years ago. By studying them, we practice a form of galactic archaeology, piecing together the history of worlds we will never see. The silence that follows 3i's departure will not be empty. It will be filled with expectation. Somewhere in the cosmic dark, the next messenger is already on its way, following an ancient trajectory set in motion before humans even existed. When it arrives, we will be ready with telescopes sharper, spacecraft faster, and minds more open to the diversity of possibilities. 3i has shown us that the universe still holds secrets we cannot yet explain, but also that we have the tools to confront them with curiosity rather than fear. Its brief passage is both epilogue and prologue, the end of one mystery and the beginning of a new era in which interstellar visitors will become familiar guests rather than shocking anomalies. The universe keeps sending us gifts. Our task is simple, though never easy, to catch them as they pass, to learn what we can, and to let them remind us that the galaxy is alive with motion, chemistry, and memory. As Atlas fades into the interstellar night, we are left not with answers, but with readiness. And perhaps that is the greatest gift of all.